Okay, hi everyone. Um, in this kind of video, I wanted to explore some of the implications of higher dimensions, and when you include, let's say, a fifth dimension, in addition to the four-dimensional space-time that we think about. And this kind of video was motivated by, as I say in the description, discussions I've had with students, math students and some physics students in particular. And what I discovered is that although Kaluza-Klein theory, which is what I will discuss here, is talked about a lot, very few people give a kind of geometrical interpretation of it. So that's what this video is. It's Kaluza-Klein kind of five-dimensional gravity theory, but with a kind of modern geometrical twist, like using Cartan forms and Cartan's kind of differential geometry. Also, so I do want to mention, so in this video, we'll be talking about, you know, Kaluza-Klein theory, which is, 5D space-time. And the idea behind it, it's so what we'll consider here is really based on the work of Oscar Klein himself. So Oscar Klein, 1926. But as I said, we're kind of giving a more kind of modern geometrical twist on it. And that is based on, there's a book that's a very good book. It's called Modern Kaluza-Klein Theories. And then, a lot of what we do is based on the GR kind of textbook, based on Herwig and Gron. It's a very kind of book, a good book. It explains a lot of GR from a kind of a modern geometrical setting. So that's what we'll do. So the idea kind of is a very simple idea, and that idea is basically that we assume that there is an additional spatial dimension that is compact. Okay. So you have a five-dimensional space-time, and we want to kind of investigate here the implications of such a dimension. So if you have a five-dimension or a fifth dimension, what does that actually do? So kind of our starting point is to consider, a 5D metric tensor. So that's what I'll do here. So, a 5D metric looks like this. So let's standard in ds squared. This time I'll use capital GAB and then dxa, dxb. So I should mention this, in what follows, so that's going to be our metric tensor, and this is a 5D metric here. And what I'll do is, so what follows, Latin indices will range from 0 to 4. So we start our index at 0, and our fifth dimension is indexed by 4, and Greek indices will be from 0 to 3. And in addition, what we will assume, that there is a spatial killing vector. And this will allow us to perform spatial compactification. All right. So what I'll do as the first step is, I'll choose a set of basis vectors. Such that, the the basis vector that represents the fifth dimension. So what else? I'll call it E4, coincides with the killing vector that I previously mentioned, coincides with this killing vector, which I will just label by the Greek letter Z. And so essentially we have an invariant basis, and that's defined by the commutator relationship, EU E4 is equal to 0, and I said mu goes from 0 to 3 because it's a Greek letter. And so what this implies, if you work it out very simply, is that E4 with the 5D metric goes to 0. So what this is saying is that the metric is independent of the fifth dimension. So you have independence of the fifth dimension. Okay, so that's going to be a useful thing that we will make use of later. And in general, what these kind of relations imply then is that you can write that. So in general, E mu dot E4 is going to be equal to G mu 4. Okay, so just kind of relationship that we will kind of make use of. And so what we can do then with these kind of spatial basis vectors, as you know, what's commonly done is we can decompose them into a parallel and orthogonal part. So decompose EU into as follows. So this is going to be EU orthogonal plus EU parallel. And in particular, what we will have is that EU orthogonal component dotted with E4 is 0. So what this basically is saying is that we will project the fifth dimension onto the orthogonal component of the killing vector. Okay, and this kind of notion of orthogonal projections is going to keep coming back to us. So it's going to be something that we use again and again and again, and we'll make use of that. So what I can do with the 5D metric I had before, so what I'm going to do now is take my kind of 5D metric here, and I'm going to rewrite this as a decomposition of a kind of spatial metric and non-spatial metric as follows. So this is something you typically do in cosmology a lot. It's kind of like doing a 3+1 decomposition, but because we're in 5D here, it's not 3+1. You can think of it as, decomposing into a 4 kind of spatial dimensions and 1 time-like dimension. So in general, we would write it like this. So let's write it as ds squared is equal to g mu nu dx mu dx nu. Dx nu. Right? And then this will be our component of a metric where the indices, as I said before, go from 0 to 3. So I'm writing it again so it's easy to kind of keep track of. And then we'll add the other part here. So G44 dy plus G4 mu over G44 dx mu squared. Okay, and this is the metric tensor that we will work with, and we'll see why this is actually a really convenient form to work with this our problem in. And so dy here then is an additional coordinate. So we will see the implication of that very shortly. Okay, so there are some kind of things that I should mention about this metric here. So small GUV, if you guys remember from just the way you do projections, you can think of small G mu nu as a projection tensor. And in particular, it's the projection of big GAB onto the orthogonal complement of E4. Okay, so then you have a simple projection tensor. So then we have an important identity, and you'll see we will make use of this identity at the end. So after we do our derivation, this identity will be very useful. And in particular, it's this. So GAB is equal to GAB minus the product of the Killing vectors. So these are Killing vectors, CA, CB. And where, as I said, these are Killing vectors. So we define as E4, and this is going to be Killing vector A. So this is just a product. So this is how we kind of expand out our Killing vector. So that's just that. And we have this G44 kind of a component here. And what's that? So let's make some further definitions. So let's define some one form A, and this is a one form. So I'll write it explicitly as a differential form in a second. But it's a differential one form with components, let's say A mu. So once again, 0 to 3. And we'll write this as G4 mu over G44. And then we'll have an additional one more definition where we define some scalar field phi, and this is a scalar, as the simple square root of G44. Okay, so all of these things will come back in great importance. But in terms of kind of physical interpretations of what these things are, so phi in particular here is the size. So this variable defines the size of the extra dimension, the fifth dimension. And A mu here is the tilt. So this defines the tilt of the extra dimension. Okay, so that's the idea. So some just basic definitions here. Okay, so now let's go into Kaluza-Klein kind of theory and use all of these kind of geometric notions to talk about Kaluza-Klein action. So the first thing that we do if we're doing a physical theory, we have to write down an action principle. So, the main action here is the Kaluza-Klein action. And that is simply given by, so S is for action. Let's say you have 1 over 2. So here the gravitational or the kind of physical constant K, which shows up in Einstein's equations, of course. I give it as a K sub 5. So this is the fifth dimensional gravitational constant. And then, it's the integral. So it's an action integral. You have the fifth dimension Ricci scalar times the determinant of our big G. And then it's with the d5x, right? Because this is a fifth dimensional action integral. So once again, this is the 50 gravitational constant. And this is the 5D Ricci scalar. Okay, so the trick here and kind of the important point is that, or the strategy I would say then, is as follows. It's to somehow relate the fifth dimensional Ricci scalar to the fourth dimensional Ricci scalar, because this is what we're used to, and this is the fourth dimensional Ricci scalar that shows up in GR, right? So Einstein's gravity is based on the fourth dimensional Ricci scalar, but in our Kaluza-Klein action, we have a fifth dimensional Ricci scalar. So what we need then is somehow to relate the two, and what we will find as we do that, you get some very interesting, kind of very beautiful result that results from relating the fifth dimensional Ricci scalar to the fourth dimensional Ricci scalar. So people who are students of differential geometry know that if you wanted to relate, so if you want to, in the classical world, of differential geometry want to relate, let's say n plus 1 curvature to n-dimensional curvature, there's a very beautiful theorem in differential geometry based on Gauss, and this is the Gauss's theorem. Gauss's theorem egregium, a beautiful theorem, and what we will derive then in what follows is something that is related to this, so something that is akin to this. So we will derive a version of this that is kind of specialized towards orthogonal projections on hyper surfaces. Okay, so that's the main idea here. Okay, so if I go back to this kind of metric tensor here, if you kind of just plug in this metric tensor with some coordinates and try to compute the connection coefficients and the Ricci tensor and the Riemann tensor and all that stuff, it's actually quite complicated. So, and people have tried to do this in just kind of general coordinate basis. And what they find is that the computations can actually get, even on a computer, like if you use Maxima or one of these kind of tensor packages, the computations actually can get kind of complicated really quickly. So what we'll do to simplify our lives, so to simplify computations, and this is where the kind of twist of using kind of modern, and by modern I mean like 100 years old modern. We're talking about Cartons formalism, which is like 1920s or 1930s. But I could be wrong, but I think it is around that. But anyway, so to simplify computations, we won't work kind of in a specific coordinate basis. We'll use orthonormal frames. So to simplify computations, let's use orthonormal frames. And so I also like to kind of mention this a lot because it's like all the work I've done in GR and cosmology has used orthonormal frames before. And orthonormal frames, so they have been around for a long time, but the approach itself was pioneered by Ellis and McCallum, and it's a very useful approach in cosmology, so in kind of cosmology, okay? So we will use orthonormal frames, and what you find is that if you use orthonormal frames with the Cartan formalism, computations of computing all the different curvature components actually become much simpler, and that's why you work in an orthonormal frame, okay? So what we'll do is let's choose an orthonormal frame. And in particular, let's call that orthonormal frame, let's just note it omega 4, and let's call it, so phi dy plus a mu, and then we'll have another differential form there, omega mu, okay? And actually, if you see, my choice for this orthonormal frame is very much motivated by the form of the metric here. So if you look into this portion of the metric here, you can actually read off more or less what is the type of differential form you want to use. So that's the orthonormal frame that you want to use. So that's kind of the main idea here. Okay. So given that orthonormal frame, let's compute the exterior derivative. So the exterior derivative is kind of a very straightforward computation to do. So what we'll do is, it's just product rule here. So I can write, let's see here, so dw4, so this is the exterior derivative, and this is equal to, let's say, so let's apply it on each component. So this is d phi dy plus d phi a mu omega mu. And of course, this term will drop out to 0 because here you'll get like d squared y, and that's equal to 0 by just what we know about differential forms. So if I continue with this calculation, you get this covariant derivative of phi v with respect to, let's say, omega v dy. So I'm just expanding out the derivatives of each of these forms, or applying the exterior derivative here, which is a very straightforward thing to do. So this is going to be phi colon v wv av w mu. There shouldn't be a covariant derivative there. Okay, av w mu, and then plus the derivative on the third term there. So a mu colon v w mu wv. And I'm using semicolons here to denote covariant derivatives, as is commonly done. So instead of using the nabla symbol, I'm just using a covariant derivative here by a semicolon. Okay, so I can then factor out the phi colon v components here. So this is going to be phi colon v, and this will be wv dy plus av, or a nu. Sorry, I have a tendency of not spelling the Greek letters or by their name. I just call it v and mu, but you know what I'm writing based on everything. So this is just going to be phi au nu omega nu omega mu. Okay, so it's straightforward. And actually, we can do a bit of a trick here. If you notice something here. So this is if we were to stop here, it would be fine. But there's something that we can consider. If you actually look at the differential form here, there's something that's very interesting about the differential form here, or the orthonormal frame here. So if you look at the orthonormal frame here, we can kind of work with this and substitute it into this line here and make another kind of substitution. And so we can write this really as omega v over, phi semicolon nu over phi, omega nu omega mu. So we can bring in that 1 over phi component just because it's already defined for us up above. So this is phi nu. Okay, and we can even make yet another simplification, because you guys know from just calculus, this component here can be written as the derivative log of phi, right? So we can even make yet another simplification, and we can write this as log of phi covariant derivative, and then just the same terms carry forward, right? So it's pretty straightforward to do this. Okay, so that's the exterior derivative of our kind of omega 4. Okay, and so let's make yet another simplification here. Not really a simplification, but let's make it a definition here. So let us define the anti-symmetric tensor as f mu nu by the following definition convention. So this is a mu nu minus a nu mu. And those of you that have done electromagnetism before right away see that this is the Faraday tensor or the EM tensor, right? So when you do covariant electrodynamics, you work with the Faraday tensor, and this is exactly what this is. Okay, so this is the Faraday tensor, and it comes into play in electromagnetism. So it's very interesting that the choice of form that I've chosen has within it this idea of the Faraday tensor that actually just pops up out of nowhere. Okay, so it's already, we're starting to see that by working in this fifth dimension, which is what this W4 is, and just taking an exterior derivative, all of a sudden we have a component or a term that shows up in the Faraday tensor or the EM tensor. So it's interesting, we can work with that. So let's look at this term here. So in our kind of exterior derivative, a mu colon nu shows up. And that's a tensor, right? Because it's a covariant derivative, so it's a tensor. So what I can do actually is I can expand that into a symmetric and anti-symmetric part. So you guys know this from the started kind of tensor calculus. So this is going to be a nu mu plus 1/2 a nu minus a nu mu. Okay. And in fact, what's going to happen now is if I now take this expansion or this kind of way of decomposing a tensor into its symmetric and anti-symmetric part, and I substitute it into here, it's going to be applied along the wedge product. And we know that the wedge product by definition, since the wedge product, so I'll just say the wedge product here by definition is anti-symmetric. Right, so that's just kind of standard differential geometry. So the wedge product here is anti-symmetric. So now if I apply an anti-symmetric product to a symmetric component and anti-symmetric component, it will turn out that a contraction on a symmetric tensor with an anti-symmetric component is 0, right? So the only thing that gets left over when I substitute it in will be this term here. So given that I can make that substitution now in my DW4. So I have kind of the very interesting result here, which I'll use a different color. So then simplifying after substitution, I get that my exterior derivative of my form is given by, so the log phi obviously is still there, and that's a good thing, right? So this wedge product, now minus 1/2 phi, and now the Faraday tensor shows up. And that's really, really, really interesting that it's there. Okay, so this is F mu nu, and this is going to be W mu W nu, right? So it's very interesting, once again, that the exterior derivative of my form actually brings together this Faraday tensor, which is really, 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 really deep. And we'll see what is the implication of that in a few moments. Right? So the EM shows up, and I cannot stress that enough, because it's really, really remarkable, this idea that we just started with this kind of this space-time metric, and all of a sudden, by just considering an extra kind of spatial compact dimension, the EM tensor shows up, which is really, really interesting. Okay, so now with all of these things that we have derived of the kind of exterior derivative, now let's start to work out some of the curvature components. So the the different rotational forms using Cartons structural equations, and then we'll figure out what the Riemann tensor components are as well. Okay, so that's the next step here. So let's now use this to figure out. So use this to figure out the 5D rotational forms. Okay, so this is a pretty easy thing to do because we have equations in differential geometry that allow us to do that. So the way we figure this is we use what is known as Cartons' first structural equation, and that is given by dWp equals to minus omega p nu rho, right? So it's not p, it's rho, but bear with me. I'm not used to speaking in Greek symbols, so I just call it as I see it. So these are the rotational forms. Okay, and we can just match. So do some kind of equation matching to see what the structural forms are, or what the curvature rotational forms are. So I can use this equation, and I can write dW4 is equal to minus 4 nu wedged with omega nu. But I already have an equation for dW4 from my previous slide here. So I already have that. So what I do is I just match the two sides and see what I get. So if you actually equate the two expressions for dw4, what you get is that the 5D form, it's pretty easy to kind of work it out, is just given by 4 mu is equal to log phi mu w4 plus 1/2 phi, and once again the Faraday tensor is there, w alpha. Okay, so these are the 5D forms, and it's a pretty straightforward thing to do that. Okay, so in some sense then we can rewrite the Cartons first structural equation as a 5-dimensional version. So let's do that. So given that the 5D version of Cartons structural equation, the first one, so first equation, I can write that as dw mu, let's say, is equal to minus. So when I put, or in GR, when you see the number in the bracket here, that's just the dimension of the form you're working with. So this is mu alpha wedged with omega alpha, and then minus, once again, the 5th dimensional rotation form for mu wedged with omega 4. Okay, and that's very straightforward to work with. So then if you actually just see, I can use this to completely compute what the 5th dimensional rotation form is, right? So in general then, using this, we see that the general 5D rotational forms are given by a very straightforward. So just do some equation matching, and you get that this is equal to, so I'll change my color because it's an important thing to write, because we'll make use of it later, as nu alpha is equal to the 4-dimensional version, so nu alpha minus 1/2 phi, once again a Faraday tensor, which I've written in mixed form because it's useful to do that later on, as you see, times w4. So this is the general kind of 5th dimensional rotational form. And why did we go through all this trouble to kind of come up with this rotational form? Is because now we can use this in combination with the general definitions of a exterior derivative. So dw, let's say rho, or dwp, or I call it p. As you can see, the connection coefficients, they show up in the definition, right? So by definition, this is rho nu mu, and then wedged with this, right? And this is clearly symmetric in these components in the bottom, mu nu components, right? As you would expect from connection coefficients. And then also we have that the rotational forms in general are defined by omega nu mu is equal to that, so mu alpha omega alpha. Okay, so by definition we will use these two definitions together, and we can use them to define or to come up with what are the connection coefficients. So using these together, these together, we can calculate the 5D connection coefficients. Okay, so let's do that. So we see that by definition that the 5th dimensional form, let's say for mu, is given by, just by the previous definition I have, Christoffel-Seymour connection coefficient for mu alpha omega alpha, and then this is equal to 1/2 phi, once again Faraday tensor omega alpha. Okay, So this implies immediately, as you can see, just by matching the two sides of the equations, that this connection coefficient for alpha, beta, let's say just changing the indices for convenience, is equal to minus for alpha for beta by symmetry. So, you can apply the symmetry arguments and change the orders of the indices, and that's the symmetry properties for such connection coefficients. And this is a half phi alpha beta. Okay. So it's interesting then that the 5D connection coefficients are completely determined by our scalar field and the Faraday tensor. It's very interesting that is the case here. Okay, so now we are kind of halfway there. We've defined and kind of derived some important things with respect to connection coefficients. So let's actually work out a little bit more, because we're not done. We still now have to come up with some expressions of the curvature tensor themselves, right? So we have the connection coefficients, but now, we still need, the curvature tensors. And we'll see that's possible to calculate using this kind of Cartan formalism as well. But let's actually just make a general statement before I do that, which will be a good hint. So the hint and kind of general statement is the following. So if I take projections of my 5D rotation forms, so let's say V alpha or nu alpha, that by definition is the fourth dimensional curvature forms. So what I'm saying is by this statement here is that the 4D rotation forms are precisely orthogonal projections from the 5D space, right? So, and we said that right from the beginning, okay? So now I can take what I will do is I will compute exterior derivatives. So now I will compute exterior derivatives and take their orthogonal projections. Okay, so that is a kind of, it's a straightforward thing to do. It's a bit of a messy kind of calculation to do, but like I said, it's better than working in specific coordinates because you have too many complications in that world. So literally I mean to do something like this. So and we want to project that exterior derivative, and this is going to be the exterior derivative of the fourth order or fourth dimensional curvature form minus a half d, and then this is going to be phi, and then I have v alpha omega 4, and then this is also going to be projected as well. And this is a straightforward thing to do, because by definition, recall that actually the exterior derivative of the Faraday tensor is by definition 0. So if you have done some work with the exterior derivatives or using differential forms in doing electromagnetism, this is one of the first properties you uncover, is that the exterior derivative of the Faraday tensor is itself 0. Okay, so it's a pretty straightforward. So if you actually carry forward this kind of differential calculus kind of operation here, you get the following expression, right? So let's actually just write it out. So this is going to be, I'm trying to see what is the best way to kind of do this. Yeah. So what we'll do also when we do this calculation is I will make use of the previous expression we have derived for W4 and omega 4 and d omega 4. So if you actually recall, we had d omega 4 as that. So any expression that has a d omega 4, I will bring in from here, and any expression that has an omega 4, I will bring in from here. Okay, so upon kind of using previous expressions for omega 4 and d omega 4 in particular, we get that this is equal to the following kind of expansion, right? So I put big square brackets because I will then take their projection. So I've still not done the orthogonal projection, but that's a very simple thing to do. So because we're just projecting from 5D space to 4D space. So this is nu alpha minus a half d phi f v alpha omega 4. So we have an omega 4 component. So that is a hint to use what we previously have derived. And this is minus a half Faraday tensor nu alpha, and then here's once again log phi. So you can see that I've already put in my expression previously derived from dw4, and that's where the log phi covariant derivative shows up again. So this is going to be omega nu omega 4, and then minus a quarter this time phi squared, f nu alpha, f nu mu, right? Omega mu wedged with omega nu. And I will take then the orthogonal projection. And once you take the orthogonal projection, you get the following very interesting result, that this is equal to the exterior derivative of the fourth dimensional rotational forms minus a quarter phi squared, f v alpha, f beta, let's say gamma. So I just switched my indices to make it more convenient for what I will need in the future, right? And that's what you get. Okay, so this result will be useful in a moment from now. Okay, so right, like I said, we're still on the kind of goal of trying to figure out what our kind of 5-dimensional curvature looks like. So don't get lost in that. We're still trying to figure out what that 5-dimensional Riemann tensor or 5-dimensional Ricci tensor looks like. So we're almost there, but we have to just use a bit more kind of differential geometry to figure out, you know, where we're going. Okay, so let's keep going. So if you recall from a differential geometry, there is a fundamental result, okay? And there's a fundamental result that says that if you take, let's say, the exterior derivative twice of some vector quantity here, then that's equal to 1/2. And now look at this, is you can start to see where I'm going, because the first component that shows up in this kind of computation of a second exterior derivative here is the Riemann tensor. So this is very interesting, but this is a general result. And if you take a course on differential geometry, kind of Riemannian differential geometry, you will immediately see that this is one of the things you derive. So we'll make use of this idea. So this is the Riemann tensor, and then you have the component of A, and then you have your basis vector, and then now we'll have, you know, the standard. So this is going to be tensor product with the wedge product. Okay, so this is actually a fundamental result for any vector A in differential geometry. Okay, so using this equation or result, and as I said, it's a very well-known result. You can use it. You can find it in any differential geometry textbook that's reasonably advanced. If you guys are interested in the comment section, you can ask, and I can point you to some really good resources on differential geometry that is actually useful for GR. Because what you find is that there are a lot of universities that offer courses on differential geometry, but they don't go beyond kind of just standard Euclidean space differential geometry. So at most you'll do like stuff with, curves in 3D or something like that, which is not useful at all for general relativity. So if you want to know how to do differential geometry for GR, I can definitely point you to some really good resources. Okay, so using this equation, I lost my slide there. We can derive what is known as the projected Riemann tensor. So that's going to be, how do you compute Riemann tensors? In general, you do things with basis vectors, so moving basis vectors around and so forth. So once again, I will take now my exterior derivative. I'll apply it twice to my basis vector here, and then I'll take the projection. And what you find that this is actually very simply, this is going to be just the fifth 5D Riemann tensor. So let's say mu v alpha b, and then E mu, because that's just following this formula that I wrote above. And then this is tensor product with the wedge product here. Okay, so that, and so we can start to see that we're actually getting in the right direction, because what we want to do is come up with, as I said, a version of a curvature tensor of our Kaluza-Klein theory. So we can find some interesting ideas here. Okay, so that's for the 5D Riemann tensors. You can see it comes from kind of computing these orthogonal projections of my second exterior derivative on my basis vector here. But I also have for the 4D Riemann tensor, so the Riemann tensor that is in, that shows up in GR, when you contract it twice, you get the Ricci scalar and so forth. We can also derive an interesting expression for the 4D Riemann tensor. And to do this, it's pretty easy to do by definition. So remember, by definition, the exterior derivative of just a basis vector is given by, E mu, and then tensor product with this rotational form, right? So that's just by definition. And then so I can come up with an equivalent kind of idea for my 4D Riemann tensor, right? So then I can look at, just using this idea. So if I, basically what I'm saying is that if I apply an exterior derivative to both sides here, you get something that's very interesting. So in some sense, E mu, or E nu, sorry, is equal to now D, which is going to be my exterior derivative. As I said, we're applying this exterior derivative to both sides here. So to do that, that's all I'm going to do. I'll just change around my indices here. So this is going to be, let's say, EA tensor product with the fifth dimensional rotation form here. And then what I'll do is I'll take its orthogonal projection, right? Just to keep the two sides the same. And now what we do is, very simply, you just apply this exterior derivative operator to the tensor product itself. So if you do that, you get just following through on the calculation that this is equal to exterior derivative of the basis vector tensor product. So it's just a product rule, right? I mean, it's very interesting that it's just the standard product rule from kind of calculus that you know of, that you just use again and again, but we're just using it in a different context. But it's the same product rule, right? So like derivative of the first times the second plus the derivative of the second times the first, it's the same idea, right? So that's all I'm doing here. So there's the second, and now I will take the exterior derivative of the first, right? It's the same idea, or first times the second, however you want to read it, but it's the same idea. Okay, it's exactly the same. People kind of get intimidated, and now I can factor out my basis vector component, and then just tensor product that with what's left, right? So that's an easy thing to do. So mu nu plus, here's my 5D rotation form, mu a, now wedged with my 5D rotation form, A nu, and once again it's the orthogonal projection. So this is a pretty easy thing to do. I mean it's not very difficult to do, but you see here something very interesting has happened, and that's really kind of the beauty of this is right here. So something beautiful has emerged here, right? So something very beautiful has emerged. And if you guys once again recognize what this is from differential geometry, this is basically related to Cartons' second structural equation, right? So what we'll do is on this wedge product here, so on the wedge product, which I kind of highlight here, let's use now Cartons' second structural equation, and that very easy thing to do. So obviously it's just an equation. So what we'll do is that on that wedge product, we recall from Cartons' second structural equation that this is equal to the Riemann tensor. So it's the Riemann tensor components that's we write as mu view, and I'll explain why it's written with two indices. So typically in kind of older kind of ways of doing GR and differential geometry, you're always taught that the Riemann curvature tensor has 4 indices. And indeed, I wrote it a few slides ago with 4 indices. But Cartons' structural equation writes it with 2 indices, and you'll see why. I'll explain it in a second. So this is actually the Riemann curvature tensor, and it's the exterior derivative of the rotational form plus, so I'll just keep going, mu lambda wedged with omega lambda nu. Okay, so here this is indeed the Riemann curvature tensor, but recall that this is written as, so r mu nu is equal to 1/2. So here's the coordinate expression that you guys know of the Riemann tensor, right? And it's wedged. It's multiplied by this wedge product. So this Cartons structural equation gives you that. Okay. So what I'll do is, and I should have been more careful about this, is that let me actually just do some labeling here to help us. So let me go back. Let me, for convenience, label this equation here that I've derived by, let's say, equation star. Okay, because it's going to be important. Okay, so I'll label that as star, and you'll see why in a second. So using Cartons' structural equation, let's combine all of these expressions together. So combining these expressions together, we come up with an expression for our second exterior derivative of the basis vector and its orthogonal projection. So we see that, let's say d squared EV orthogonal component. So it's going to be equal to 1/2, now the 4-dimensional Riemann tensor, okay, minus 1/4 phi squared, 2f mu nu f alpha beta plus f mu alpha of beta beta, right? And then this is going to be multiplied by E mu tensor product omega alpha omega beta, okay? And I will call this equation, I will call it equation double star. And so what you're seeing is why I did this. If you look at equation star, which is also an expression for the second exterior derivative of this basis vector and its orthogonal component, we also have 1 here. So what I do is I just compare the 2 equations here, right? And you can start to see immediately where I'm going to go by doing this. So if I compare equation star in equations double star, you get a very, very beautiful result, right? And that's the result that we were seeking. So let's write it down. I'll use a different color because it's a very, very beautiful result. We get that the 5D Riemann curvature tensor, so mu v alpha beta, is equal to the 4D Riemann tensor. So here we go, right? This is what we wanted. We wanted our 5D Riemann curvature in terms of its 4D counterpart. Because I don't know off the top of my head what 5D physically means. All I know from physics is that the 4D curvature leads me to Einstein's gravity. So I have my 5D action, but now I can write it in terms of my 4D curvature, which is what gravity is, right? So mu alpha beta, that should be mu alpha beta minus 1/4 phi squared 2f mu beta. So it's just rewriting the terms, right, again. So just breaking them together. So it's nothing really new here. It's just results from comparing to the two star and double star equations. Okay, so you can see this is a very, very, very beautiful result that has resulted. So here, this is actually a version of Gauss's Theorem egregium. And what we are able to do, it's a very remarkable idea. We have here 5D curvature in terms of 4D curvature. But what is very interesting, so let's actually, before I kind of say what I want to say, let's actually keep going, because in Einstein's equations, you don't have the Riemann tensor, you have the Ricci tensor and the Ricci scalar, right? So let's, and indeed our action principle, if you go back from like the, let's see, what slide did I write the action on? Here, the action principle is with the 5D Ricci scalar, right? So it's not the Riemann tensor, it's the 5D Ricci scalar. So obviously it's not very difficult at all to go from here and get a 5D Ricci scalar. So all we will do now is contract, right? So anytime you have a tensor and you want to get a scalar, you just contract on the indices. So that's what we will do now, okay? So, I'll contract separately. So what I'll do, I guess that would be the easiest thing to do. So what I'll do is I'll contract of this expression here, the left side separately from the right side. So let's work on the right side, which is this side here first. So once again, so let's contract on the right side first. So what I'll do is I'll contract twice, actually, because one contraction on the Riemann tensor gives me the Ricci tensor, and then another contraction on the Ricci tensor gives me the Ricci scalar. So let's contract twice to get a Ricci scalar. And indeed, what I'll get when I do that is, when you do that two contractions, you get the 4D Ricci scalar minus 3/4 phi squared, and then alpha b, f alpha b. Okay. I don't know why the box disappeared, but okay, that's fine. And for the left side, it's slightly more complicated because you have this 5D thing here, but to contract the left side expression, what I'll do is I'll contract in terms of the projection tensor. So if you remember way back, like about half an hour ago, 20, I don't know how long I've been speaking for, but half an hour ago maybe, we introduced the projection tensor, and now this is why. So what I'll do is I will contract the left side expression in terms of the projection tensor. Okay, so what I mean literally, and that projection tensor, if you remember, is GAB, right? And it was given in terms of these killing vectors. So in a sense, what I'm saying is that I want to compute, here's my 5D Riemann tensor. So let's give it those indices because it's 5D. So let's GAE, and now we apply the projection tensor, which is a small g metric, to essentially each index. So I'm contracting over each index here, and if you go through this, this is just equal to so REFIJ. So the first one, by the definition of my projection tensor, which I gave quite a few slides ago, and here's my killing vectors here. Okay. And this is going to be GFJ minus killing vector F killing vector J, right? So then this is pretty easy to work with because now I can do this full out contraction. It's a very straightforward thing to do. And if you just go through with this calculation, you get a very interesting result. So you get that this is equal to the 5D Ricci scalar minus 2 Ricci tensor, but contracted with the killing vectors, which in itself is very interesting that this pops out. So that's why I wanted to do the two sides separately, is because you find out this expression, that you're left with this contraction. So the question is, what is this contraction here? So it's actually very easy to kind of see what that contraction is. Because if you recall how to compute, how to compute the covariant derivative of these killing vectors, and that's given by, so let's say, this is just a standard kind of formula in differential geometry, or you see it in GR all the time when you discuss Killing's equations. So that's the connection coefficient there, right? So it's actually pretty straightforward to do that. And I think I made a mistake on the indices. So it should be... No, I think it's okay. This should be B. Yes, that's the right formula. See, I knew I made a mistake because these indices were not matching. Now all the indices lined up, so it's good. Okay, so this derivative is just equal to minus that, minus gamma 4BA, which is just the connection coefficient. So then, given this, it's very easy to show that contraction that we were kind of temporarily puzzled with, but now we kind of know what it is because we have this definition here. This is equal to 1/4 phi squared f alpha beta minus 1/phi. And here's my D'Alembert operator. So it's very interesting, the D'Alembertian of phi. So here you get that here box is the D'Alembert operator, which is just a wave operator, right? So those of you guys that have done some special relativity before and have looked at the relativistic wave equation have definitely, or even if you've taken a course in PDEs, have definitely come across the D'Alembert operator before, right? So this is just a D'Alembertian operator. So it's very interesting. Now another thing that's popped up here is that in our kind of quest to derive an action principle for our 5D theory here, you get a wave, something that looks like a wave equation for y. So, this is the kind of relativistic wave operator that you guys see in PDEs all the time. And so what we're seeing is that this wave operator actually shows up in my gravity theory. So this wave operator that determines kind of propagations or dynamics of this scalar field. And remember what we said about this scalar field is that this scalar field determines the size of the extra dimension. So that is kind of an interesting thing, that extra dimension's dynamics in terms of its size dynamics is governed by this wave equation, which is really interesting. And you can't see my face, but I'm smiling every time I go through this derivation because it's very, very, very interesting. So now we're there, right? So now we have our 5D scalar we have our 4D scalar here. So now I'll just bring them together. So once again, I just take this expression, and I bring them together, and now I have that an amazing result. So let me use a different color. So then we have the remarkable result. And that remarkable result. So the 5D Ricci scalar is given by the 4D Ricci scalar minus 1/4 phi squared f alpha beta minus 2/phi D'Alembert of phi. This is the most remarkable result that we've ever. I mean, obviously it's and let me kind of explain this. So let's go back to our action principle that we started with. So let me go back to the action principle. So the action principle, if you remember, was, how did we write it? If you recall, it was S is 1/2 kappa 5 times 5 the 50 Ricci scalar times this determinant of the 5D metric. So our Lagrangian, which is what this is here, it's our Lagrangian. So what we're saying is our Lagrangian for our theory here is given by, and here to write this expression, so recall that the determinant of my 5D metric is given by phi times the determinant of the projection tensor, or the 4D metric, right? So phi minus g, 4D Ricci scalar minus 1/4 phi squared f alpha beta minus 2/phi D'Alembert of phi. So this is one of the most amazing ideas. And if you look at this 5D theory of gravity, what you hear here is some interesting results that pop up. So the first term here is the regular 4D gravity, Einstein's GR. Then in this term, you have electromagnetism, right? So electromagnetism. And here you have the scalar field that determines the size of the extra dimension, the fifth dimension. So what we conclude is that in the 5D gravity is that 4D gravity, or the gravity that we experience as humans, is equal or equivalent. Or instead of, I don't like the word equivalent because that could have some, technically it's inequivalence, but I mean, let's say unified. So 4D gravity is unified with electromagnetism. And that is at heart the Kaluza-Klein theory. So once again, it is a remarkable idea that if I take 5D gravity and I kind of do some curvature calculations where I'm essentially saying, okay, what is the fifth dimensional version of the Ricci scalar in terms of stuff that we know of? So as humans, we can only experience up to 4 dimensions, right? So 3 spatial and 1 time dimension. So it's very interesting that what we're seeing is that in the fifth dimensional or theory or 5D gravity, classical gravity that we experience is unified with ENM. And that's very deep, actually, this idea. And it's nothing fancy. Like, we've not resorted to string theory or any of these kind of very higher dimensional theories. Like string theory, I think, though, some of the motivations for string theory, at least in terms of geometry, can be justified by doing this type of Kaluza-Klein theory, right? But that's a separate topic. But this idea that 5D gravity implies a unification between regular old 4D Einstein gravity and electromagnetism, and the fact that these two forces are unified. So remember, one of the grand dreams of physics is to unify the four forces, right? So the weak force, strong force, E&M, gravity, and so forth. We want to unify those forces, and now we're saying the way you unify gravity and electromagnetism, two forces that seem completely different from each other, the way to do that is by looking at higher dimensions. So that is very interesting. And if I was to kind of carry on with this derivation, although the derivation itself is done, but if I was to carry through with some more calculations to see how you can compactify this fifth dimension, what you start to see is that actually you can show that the fifth dimension itself is very small. It's predicted to be very small. I think less than 10 to the minus 30 centimeters. So that's why we can't even experience it as human beings, is because it's so small. So at least from a Kaluza-Klein, from kind of standard old general relativity that we obviously know to be true, and electromagnetism, which we know to be true, if we kind of take it in 5 dimensions, we start to see that these two forces are unified. And that is I can't stress how, even if it physically turns out to be experimentally unverifiable, I think mathematically it's still a very beautiful result. So yeah, so thanks for watching. If you guys have questions, then please let me know in the comment section, or you can contact me of any way you want to contact me. That's fine. Okay. Thanks for watching. Until my next video. Have a good day.